All right. So somehow last week I wound up the class a bit earlier on Tuesday because somehow I assumed I forgot that we start at an odd time, 3:25. So I could have gone on till 4:40 technically. But anyway, maybe it would have been information overload to go on for that long also. So let's quickly recap what we did last time. As you know, last week we started introducing quantum error correcting codes. We discussed the 3-bit classical code and we looked at what are the challenges in naively extending it to a quantum code. And then we looked at ways to overcome these challenges. And that's how we arrived at the 3-qubit code, very much inspired by the classical 3-bit error correcting code, right? So this is what the 3-qubit code does essentially. It takes you from a single qubit space through a space of 3 qubits. However, it takes you only to a two-dimensional subspace of the 3-qubit space, which is C2 tensor C2, right? And this 2-qubit subspace is essentially spanned by these two states, the all 0 and the all 1 in that space, in the 3-qubit space. And so an arbitrary state of the form alpha 0 plus beta 1 gets mapped to alpha 0, 0, 0 plus beta 1, 1, 1. So for example, the plus state, the encoded version of that would be a 0, 0, 0 plus 1, 1, 1 over root 2. The minus state, encoded version would become 0, 0, 0 minus 1, 1, 1 by root 2. Okay, this is the definition of the 3-qubit code. Now let's look at a circuit which captures the complete 3-qubit error correcting protocol, right? So this is the full protocol, okay? And this shows you exactly what is required to implement a 3-qubit error correcting code, right? So like I said, at least for much of this error correction segment, we will assume that this first part of the circuit is ideal. Actually, we will assume that all operations are ideal, right? So it's as if the error steps in or acts only after we have done this encoding. So let me divide up this circuit into 3 parts. There is first the encoding part. So I have to do that with a slightly different color. Let me see if that works. Yeah, okay. So this is the encoding. So I drew all of this separately last time, but I just wanted to show you how we can put it all together into a simple circuit. And those of you who are enthusiastic and you already have accounts can actually go and run this on a platform like IBM, right? All right. So this is the encoding circuit. The first, I'll just call these registers 1, 2, and 3, right? So first register is simply the data qubit. And the other two are actually ancillary qubits, but they are part of the encoded qubits. So we will call this set of 3 qubits out here as our encoded qubits, right? So up till here, what I have is what I will call the encoded state. And then there is the error channel acting on this encoded state, right? And so this, what the state here is what? It's something like this, right? It's alpha 0L plus beta 1L, right? That's what is the state here at this point. Okay, and then after this box which says error, you actually have the errored state now, right? So what you have post this out here is now a different state, right? So this is the state you will get after you act a 3-qubit bit flip channel on this encoded state alpha 0L plus beta 1L, right? That is the state here. And now the question is, what do we do next? So the next part of this circuit is the so-called syndrome extraction circuit. So now comes the second part of this circuit, and this is the error detection and error correction parts, right? So from here on, what you have is error detection and correction. And how do we do that? We have to first extract these two classical bits, which are called the syndromes. Was there a question? Okay. If there's a question, please speak up. So S1 and S2 are the so-called syndrome bits, right? They're classical bits. And the way you get these syndromes, which are basically the indication, which tell you, first of all, whether there is an error, and second, where the error occurred. This you do by adding two ancillary qubits here. Over and above the three encoded qubits, you now have the ancillary qubits, right? And you have to now get the information about the error without collapsing your encoded state. That's the whole point. And that's why you use these C knots to act on these ancillary qubits. And we have discussed this now both for classical and quantum bit flip code. What you need to do is pairwise parity checks. And the pairwise parity checks happen by doing this, by acting these pairwise C knots here, right? So this pair checks for the parity of these two, and this pair checks for the parity of these two. And based on this pair of classical syndrome bits that you have, we can essentially diagnose the error, right? And based on our error diagnosis, these two blue lines here are classical lines, right? They basically, there is now classical information which feeds from the ancilla qubits back to the data qubits. And what this recovery box out here is indicating is you now have to go back and do something to your encoded qubits in order to correct for the error. Up to this part is what we had discussed on Tuesday, where you extract these two syndromes S1, S2. And then what do? You diagnose the error, and then based on that diagnosis, you go back and do something to the data qubits. What is the something that you have to do? Well, it's simply a single qubit X operation, right? Because what can this code detect for? It can detect for single bit flip errors. And once you have detected where the error is, you simply go back and fix it by undoing the X operation, right? The error operator here is a unitary operator. So what this recovery does is simply a single qubit X gate, right? Depending on what the syndrome bit said. So let's go back and draw the syndrome table. So I can now draw this. Any questions as far as this circuit is concerned? Okay, so this is what the syndrome table will look like. So you have S1 and S2. And based on this pair of values, you have the diagnosis. Of course, I should mention that these measurements are Z basis measurements, right? So you're measuring in the standard 0, 1 basis. There's the diagnosis, and then there is the recovery, right? So once you've detected, you need to correct, and the correction in this case is simply a single qubit X operation, right? So if S1 and S2 are both 0, then it's no error. We already discussed this last time. So the recovery operation is simply the identity gate, right? If S1 is 1 and S2 is 0, which means that the first ancilla alone has flipped, which means something has flipped in the first two qubits, first two encoded qubits. So this, and then the second ancilla is 0, right? Which means that nothing has flipped as far as the second two qubits are concerned. So this is then a bit flip error on the first encoded qubit. And this requires a single qubit X gate on the first encoded qubit. That's the recovery operation. That's what you need to fix the error. In 0, 1 similarly means a bit flip on the third encoded qubit. And so this then is an identity X, identity X is what you need to apply. And then the last one is just the 1, 1, which is with flip on the second encoded qubit. This is identity X identity. Okay. So this table and the circuit together completely summarize what the 3-qubit bit flip code does, right? It only promises to detect and correct for single qubit errors. And we've already seen, I think, how when you have multi-qubit errors, when you have 2-qubit and 3-qubit errors, they are going to overlap with the single qubit errors. So we saw that essentially the single qubit errors map. So let me just reintroduce the technical terms now. So remember, you have the code space, in this case, C, which is a span of 000 and 111. So what is the projection operator on the code space? So let's do a little bit of this analysis. So the code space comes with an associated projection operator, or is, sort of defined in some sense, characterized by an associated projection operator. What is the operator that projects onto the code space? So what do I mean by that? Remember, I drew this cartoon sort of picture last time where I have the larger 3-qubit space and I'm sitting somewhere inside that, right? This is my code space, right? So this larger space has all possible 3-qubit states, and I'm sitting here inside the code space. So what is the operator that will take me, let's say, from any part of this 3-qubit space into the code space? So what is the operator that will project me down to the code space from any other part of this larger Hilbert space, this 3-qubit space? So I'll call this as P. This is nothing but a projection on the code space 0 and the code space 1. So this is the logical 0 in the code space. This is the logical 1 in the code space. Just like how a projector onto the single qubit space, your regular C2, what is a projector onto the regular C2 space? That is just identity on C2, right? That's just 0, 0 plus 1, 1, right? If all you have is that single qubit space, it doesn't make sense to call it a projector. But now you have a larger space and then you have a subspace of this larger space. So you can define a notion of a projector that projects down to that subspace. And that is nothing but a projection onto these individual code words added up together. So this is effectively like identity operator on the code space. And any other 3-qubit state that this acts on, you see it will project it down to some linear combination of 0, 0, 0 and 1, 1, 1, right? So why is it a projector on the code space? So if psi is an arbitrary 3-qubit state, then P acting on psi will always end up being some alpha 0, 0, 0. So let me call it something else. A 0, 0, 0 plus B 1, 1, 1, where A is nothing but the overlap of 0, 0, 0 with psi, right? That's the projection. And B is the overlap of 1, 1, 1 with psi. So this is what I mean by a projector on the code space. It's useful to think in terms of this projector because now you can go ahead and see what these different errors do. And I think I drew this picture also. This picture becomes important to understand because this is what will help us identify error correction conditions, right? So when is a code an error correcting code for a particular kind of noise? So this is what will help us identify that. So the point is that this code space now gets mapped onto different non-overlapping parts of this 3-qubit space. We already saw this. So there is a part that the XII error will map it to. There is a part that the IXI error will map it to, etc. But these are all non-overlapping parts of the space. In fact, in a way, they completely divide up the space in this case. So I think I'd done this last time where I had drawn it like this, and I said each one maps you to a different part of this, right? So the XI will map you here, the IXI will map you here, the IIX will map you here, and the identity, which is no error, will map you here, right? And once you have, and since you have now covered the entire space, there is no more room for any more errors, right? In the sense, there is no more room to detect any other errors, because the set of single qubit and no qubit error has completely divided up the space. And these now correspond to non-overlapping parts of the space. A more precise way of saying it is that you can associate projectors. So I will call this P1, P2, and P3. And this I will simply call PC. Okay. This is the projector on the code space, right? Now you have 3 other projectors associated with 3 other subspaces into which these single qubit errors map you to, right? So which are these? So the single qubit errors map to non-overlapping subspaces. So for example, let's look at IIX. What does this do to the code words? So under this, the 000, 111 will get mapped to 001, 110. So I don't know which one I call P1, whether I call this P1. No, I call this P3. Okay. So IIX is what I call P3. Oops. So the projector P3 associated with this subspace. So this is another two-dimensional subspace of C2 tensor 3. And the projector associated with this is simply this, right? 001 plus 110, 110. So then there is, I'm just listing out these things. So there's identity, X identity. This will map your code space to the space which is spanned by 010 and 101. And the associated projector is simply this now, right? And then you have the third one, which is XII. I think this is what I call P3, is it P1? Okay. And this projector is simply going to be 100 plus 011, right? Because it maps the code space to this subspace. All right, so these are 3 non-overlapping subspaces, and associated with them, you have 3 projectors, P3, P2, and P1. So effectively, the error detection happens via a projective measurement comprising of these four projectors. One is the projector on the code space itself. That is to account for the no error case. And then you have P1, P2, and P3. So you kind of analyze the whole process algebraically now. Of course, I gave you a circuit and I broke it down as ancillas and syndromes and all of that. But underlying this algebraically, what are we doing? On this larger space, this 3-qubit space, we are performing a projective measurement which identifies for us which of these four subspaces the final state is in. And once we identify which subspace the state is in, there's nothing more to do, because you simply have to, because you know that now so this is the whole point, right? You know nothing about the encoded state itself, right? Because these projective measurements are not telling you anything about the encoded state. They're only telling you whether an error occurred on the first qubit, the second qubit, or the third, or whether there was no error at all. And that's all the information we need. And we kind of blindly go ahead and do this recovery, which is simply one of these four operations. That's all. So nowhere in this have we extracted any information about what the superposition state is, what the encoded state is. Okay. Now, of course, I said there is no more room for any more errors that this code can detect, because it has divided up the entire 3-qubit subspace like this. So now what, clearly this procedure is not a perfect code as far as all the 3-qubit errors are concerned, right? It's only going to detect and correct for single qubit errors. So I hope you realize that if there was a 2-qubit error of the form IXX, for example, then the 00111 would go to 011100, and that is nothing but this, right? 011100 is what is sitting here. So you will confuse between the single qubit XII error and the 2-qubit IXX error. So we've already done this analysis. I don't want to go back and repeat all of that. But the point is, the 3-qubit code only detects and corrects for single qubit bit flip errors. Okay. Now, how useful is this? Because it's not as if there's some way for us to prevent the 2-qubit and 3-qubit errors from happening, right? So the logic that was given was, well, the single qubit errors are much more probable than the 2-qubit and 3-qubit errors, right? How much more probable? And at what point does the code actually stop working well, right? So we need to now quantify the performance of this error correcting code, and this performance analysis will hold for any of the error correcting codes that we discuss subsequently. So what I've shown you so far is that there is a simple way to do the encoding and the detection and the recovery, and that this encoding, detection, recovery all works fine so long as you're interested in detecting and correcting for single qubit errors. Okay. Yeah, I see a question from Nilesh about the projectors. I'll come back to it. Let me discuss this performance analysis a little bit, and then we'll go back to this projectors picture. We'll keep revisiting the projectors picture anyway, because when we'll start doing abstract algebraic conditions for error correction, at that point, we'll have to revisit this anyway. Let me come back to the end of the lecture, because I want to talk a little bit about fidelity and all that. So let's do a naive performance analysis, which means we'll simply ask, when does this error correction procedure fail? It fails when the the 2-qubit and 3-qubit errors actually become more probable in some sense than the single qubit error, right? So let us look at probability that only single qubit. So let me put it this way. So what is the probability that bit flips occur in fewer? Was there another question? Okay. in 1 or 0 qubits. So what is this probability? The probability that bit flips occur only in single or no qubits. This is, so if you remember the channel itself, so let's maybe quickly, I'll just write down the channel again. So the 3 qubit, actually let me just write down the single qubit bit flip channel. So this is a channel with Krauss operators. So I'll just call this is how I write this usually. So this is square root 1 minus p identity and square root px, right? These are the Krauss operators. And then the 3 qubit channel is simply the tensor 3, this, with all possible combinations. Remember, we wrote down all of this in the last lecture. I don't want to rewrite all of that again. So now, what is the probability for no bit flip error to occur? This is 1 minus p the whole cube. What is the probability for single bit flip error to occur? So that is p times 1 minus p the whole squared, right? And this comes with a 3, right? So this is nothing but 1 minus 3p squared plus 2p cube. So therefore, so in all of these instances, whenever there is a bit flip that's occurring only in one or none of the qubits, then we know that the code works. That's what we've just demonstrated, right? So what is the probability that the code doesn't work? What is the probability of errors remaining uncorrected? Because all of these errors are going to be corrected, right? So what is the probability for there to be uncorrected errors? Yes, that is 1 minus this, right? So that is 3p squared minus 2p cube, right? Now consider a single unencoded qubit. What is the probability of a bit flip error in this? Is there a problem with my audio, guys?
No, ma'am.
Yeah, I just got a message from my my laptop, so I was just wondering. Okay, all right. So you can hear me fine. So probability of error in this case, that is p. So what is the probability of no bit flip error in this case? That is 1 minus p. So what are the two quantities that we have to compare now to decide whether one must actually invoke the error correcting code or not? When does doing this entire error correcting protocol actually pay off? So I've written down some 4 probabilities here. What are the two things that we have to compare? So after doing the whole error correction procedure, there's a certain probability for errors to remain uncorrected, right? So long as this compares favorably with the error probability of a single qubit, then we are fine, right? So do you see that? Do you see that now the probability of something to remain uncorrected goes as 3p squared minus 2p cube? Whereas if I'd had a single unencoded qubit and there was a bit flip which was undergoing bit flip noise, which was subject to bit flip noise, then this is what the error probability would be. So both of these, I can call them as the error probability, right? This, except that this is the encoded case and this is the unencoded case, and we have to simply compare these two, right? Whenever the error of the unencoded case is smaller than the single qubit probability of error, so let me say that the code or the QEC is successful or even useful, provided this encoded error probability is less than P. P is often called the physical error probability, right? Physical, because this is what the bare unencoded qubit is seeing. This is the extent of noise that the bare qubit is experiencing. And in some sense, this is the extent of noise that the encoded qubit is experiencing. And this is also often called the logical error. So if you go ahead and read papers and they will talk about physical error rate and logical error rate, this is what they mean. That we say that QEC is useful provided this condition is met, that the encoded error rate or the error probability should be smaller than the physical error probability, and then this whole, it's worth the effort, right, doing all of this. So when is this true? For the bit flip code and the single bit flip noise, this is true. Oops. When 3p squared minus 2p cube is less than p. So what is the condition for p? Can you quickly work this out and tell me?
Less than 1 by 2.
Less than?
Half.
Half. Very good. And if you notice, even in the classical case, I might have mentioned this. I don't know if I did this error analysis like this, but this is exactly the same as the classical repetition code, the 3-bit repetition code. That so long as the error probability is less than a half, we know that this particular code and this particular protocol, QEC protocol, is successful and useful. So this is often called an error threshold. It's a certain level, it's a certain noise level above which error correction fails. If your noise is such that this P is greater than half, or if the single bit flip probability is greater than half, you might as well leave the bare qubit as it is. At that point, error correction is not going to help you. The encoded error rate will not be less than the physical error rate, right? So this is one way to do this analysis, but this is still a slightly naive analysis based on simply the noise model and the error probabilities. A more rigorous analysis would be to invoke a certain measure called the fidelity. So I will introduce this measure formally, although I think I gave a problem based on this in tutorial 1. So any questions? Okay, so I think Nilesh had a question about these projectors. Let me go back to that. So yeah, what I was trying to say is you have these 4 different Krauss operators, right? The all identity operator, the single X operator with X occurring in each of the 3 different locations. And these 4 error operators map your code space to 4 distinct spaces inside the larger 3-qubit space. You can associate a projection because each of this is now a 2-dimensional subspace, right? So a 2-dimensional subspace has a simple rank 2 projector. It's like a single qubit identity operator, except it's an identity operator on the encoded space. So you now have these 4 projection operators. Of course, I should have mentioned, I got carried away in the discussion, that these 4 projection operators are mutually orthogonal, right? So these are all mutually orthogonal projectors. So this is reminiscent of how you would build a standard projective measurement. How do you build a projective measurement? You probably used to just rank 1 projectors, right? You probably used to like ket 0, bra 0, ket plus, bra plus, ket minus, bra minus. So plus minus is one projective measurement that you know, 0, 1 is another. You can construct other such projective measurements, right? Probably you're used to viewing it in terms of rank 1 projectors constructed out of single pure states. Now I'm extending that idea to talk about a projective measurement with projectors which are slightly higher dimensional objects, rank 2 objects, and they are operators that project down not to a single state. They project you to an entire space, a two-dimensional subspace of this larger space. Okay? Is that idea clear? So the fact that these projectors are mutually orthogonal goes back to the fact that these subspaces are non-overlapping. Okay? Nilesh, does that answer your question? Okay, cool. All right. So, yeah. So we did the naive analysis and we have identified an error threshold. We have identified an error probability below which the code works well, above which it does not work well. But this does not tell me how the code protects or preserves the information in a given quantum state, because this whole analysis is done without any reference to states. So instead, what I would like to do is have a state-based measure of how effective an error correcting code is. Okay. So to do this, I would like to compare the initial state, which is a state that you prepared and that you want to use for your computation, and the final state after the QEC protocol. Okay. So I have, let's say I start with a state psi. Typically we start with pure states, which is what we use for our computation, right? And after the action of everything, right? So after encoding, noise, and I will simply call it decoding, but this is the entire thing, error detection, correction, etc. And including mapping back to the single qubit space, you have at the end of the day some density operator, which is the final state, right? Although you start with an initial pure state, remember that the noise makes sure that what you have at the end is going to be a density matrix. It is not going to be, because it's a stochastic process. We've been over this over the last few weeks. What you're going to be left with is not a pure state, but a mixed state or a density operator. So we need to find a measure to quantify how close rho is psi. We need to be able to answer this question of how close is the initial state to the final state, or how close is rho to the state that you started with, which is psi, right? And the way to do that is using this measure called the fidelity. So I think I might have defined fidelity in a very simple way in the tutorial. I think I defined it, but anyway, we'll go back to this. So now this, as I said, is a very important question in quantum information in general. How close are two quantum states? Rho and sigma. So let's start with a more general question, okay? And all of chapter 9 of Nielsen and Chuang addresses this question in various ways. I encourage you to read this because I will not have time to go over all of this. But I will define one measure called the fidelity, okay? F of rho comma sigma, okay? And this is the measure we will use to quantify the performance of an error correcting code. So this is defined as follows. It is defined as trace of the square root of this operator, which is rho to the half sigma rho to the half. Okay. So this looks like a very strange measure. So what are you doing? You have these two operators, rho and sigma, and you're saying that you're taking this, making this operator out of that, which is rho to the half, sigma rho to the half. Whatever is inside here is a positive operator. I hope you see that already, because sigma is a positive operator and the half always denotes the positive square root of the operator. And then you have, so you take the square root of that and you take the trace. So let us note a few cases for this. Let us do a few simple um, cases or examples. So let's first look at the case when one of these states is a pure state. Okay. So then I'm interested in the fidelity between a pure state and a mixed state, right? So this becomes trace of square root of, remember this is just a projector, right, onto the state size. So the square root of this is the same as itself, right? So this looks like this expression, and I hope you can see that this is nothing but, let me write it like this. It's trace of square root of psi sigma psi psi, right? So I've taken this part out. That's just a number. That's just the expectation value of the operator sigma in the state psi. And then this is followed by a projection onto psi itself. And then there's a square root and the trace. Now this is just a number. So this is the same as trace of psi, right? Times this number, which is square root expectation of the operator sigma in the state psi. And so this is nothing but square root psi sigma psi. So I hope you see this. So I'm going to now define something called f squared of psi with sigma is this function, which is just the expectation of the operator sigma in the state psi. So this itself should make intuitive sense, right? You're asking how close is this initial pure state. So we come back to the error correction scenario, right? Where the initial state is a pure state psi and the final state is a mixed state sigma. And this is the case that's going to be most relevant to us. So what this is saying, so I can rewrite this in fact. So I've taken now the square root, the square of this to get rid of this pesky square root out here. You see, what is this? This is nothing but trace of sigma with psi. Remember, we did this rule, we did this exercise, right, in the last semester's thing, that when you have this expectation, it's nothing but trace of these two. So this is what is often called a trace overlap. And this makes perfect sense that the closeness of this final state or this mixed state with respect to this pure state is nothing but how much of this mixed state has an overlap with the pure state, right? It's as if you are, if I were to expand this in the basis, eigenbasis of this mixed state, it's essentially capturing how close is each of these eigenstates with respect to the sigma state, and it's taking a sum of that, right? So the point is, okay, so now let's go one step further and say, what if both of them are pure states, right? So one of them is a pure state is this. It's easy to see what it is if both of them are pure states. What should you get back if both rho and sigma are pure states? So if sigma is also a pure state, then you should simply get back the overlap function, right? Which is the inner product. Then you see that f of, it's like f of psi phi, right? And what is that? That is simply square root. So you go back to this expression now, right? You go back to this star expression here. Replace sigma with a pure state phi, and then you have psi phi mod squared. So from star, okay, and that is nothing but modulus of cipher. So now you should understand why we have the square root. We have the square root to take this, to get rid of the square that you get, right, when you take the overlap of two density matrices. So if I just had a pair of pure states, how would I define their closeness? I would indeed take the inner product of those two states, right? This is the inner product. And of course, I will take the modulus because this is a complex quantity. This is not going to measure anything for me. So I will take its modulus. So this measure eventually gets me back the inner product, which is the natural overlap function or the natural measure of how close two pure states are. So if I just had pure states, the inner product would suffice. But even if one of them is mixed, then I need to go to something like a trace overlap like this. And indeed, this measure that I've written out here, which looks very complicated, reduces to these simple cases of just the inner product when it's a pair of pure states, and it's just the trace overlap or the expectation value of the mixed state in the pure state when you have one state being pure and the other being mixed. Let's now look at other cases. So if rho and sigma commute. So if I have to claim that this is a measure, then this number has to have some reasonable limiting cases, right? It should lie between 0 and 1 and things like that. So does it do that? So I will leave some of these things as a tutorial for you, but I just want to point out a few things. So when is this? Okay, so let's look at, okay, so let me look at the so-called limiting cases first before I look at the commuting case. So let me say limiting cases. So what are the limiting cases? So when should this measure? So I'm going to show you that this measure lies between 0 and 1 somehow. Okay. When will it be 0 and when will it be 1? Yes.
When they're the same state and when they're orthogonal.
Exactly. So that has to be the two limiting cases. In fact, I had given a problem like this in the end semester exam, if you remember, where I had actually that was a different measure of closeness of two states. So what you worked out in your QCQI and SEM, those of you who took it last semester, was actually a different measure called the trace distance between two states, right? That also had these limiting cases. So if rho, so let me say if rho is equal to sigma. So let's look at this before we do commuting and all that. Then what is f rho sigma? This is trace square root rho to the half sigma rho to the half. So that becomes sigma to the half sigma sigma to the half. It's all, it becomes sigma squared, right? Which is then trace sigma, which is 1. Correct? So if rho and sigma are the same, the fidelity is 1. Perfect. Makes perfect sense, right? Now, if rho is orthogonal to sigma, then what happens? You can write down rho as some Ri, Ii, and sigma as some Sj, Ej, Ej. What does it mean to say that two density operators are orthogonal to each other? You all understand what it is when two pure states are orthogonal to each other. But when I say that two mixed states are orthogonal to each other, so what have I written down? I have written down the eigen state decomposition. I've written down the spectral decomposition of these two density matrices. What does it mean to say that rho is orthogonal to sigma? It means that these eigenstates are mutually orthogonal. Another way of saying it is that rho and sigma have orthogonal support. They do not have support on the same parts of your Hilbert space, right? So this is the set of states on which rho has support, and this is the set of states on which sigma has support, and those two must be mutually orthogonal, right? They have orthogonal support. Another way of saying it would be that trace rho sigma. So what would be trace rho sigma? When they are orthogonal. Remember, trace of A dagger B is a measure. It's like a inner product between two operators. We had defined this Hilbert-Schmidt inner product, and this is how we checked, for example, that your Pauli matrices satisfy some properties, right? Yes. What is trace rho sigma?
0.
This is 0. So this is 0 for a pair of, so this is what we call the Hilbert-Schmidt inner product between operators. So you see this measure, which is trace square root. So therefore you will now agree with me that f of rho sigma, which is trace square root rho to the half sigma rho to the half, you can now show based on everything else that I've told you here, you can rigorously show that this is 0. And in fact, you can show that it is 0 if and only if rho and sigma are orthogonal. I'm just writing it like this, okay? So these are the two limiting cases. So one can show that this measure is something that lies between 0 and 1, and it is 0 if and only if rho is perpendicular to sigma. It is 1 if and only if rho is the same as sigma, okay? And everywhere else, it is some number between 0 and 1, and therefore it is a valid measure of distance between states, between quantum states. So if we were only dealing with pure states, I repeat, then it suffices to just think of the inner product itself gives you a metric actually on the space. If you're just concerned with pure states, but you're not concerned with only pure states, you are interested in mixed states, and then you have to look at when are two density operators orthogonal, and that leads you to the trace overlap function, this kind of a Hilbert-Schmidt inner product, and inspired by that you have this measure. The square root, as you can see, makes sure that your limiting cases are recovered. In particular, it says that when the two are pure states, the overlap function itself, the inner product itself, becomes the fidelity function, right? So fidelity 0 means these two states are mutually orthogonal, they don't have common support. Fidelity 1 means that they are exactly the same state. The last case I want to discuss is the case when rho and sigma commute. So this is the case of commuting operators. And it turns out that this actually leads to a classical measure of distance between probabilities. So that's why I want to talk about this case as well. So when rho and sigma commute, what happens? It means that they are diagonal in the same basis, right? You can find a common eigenbasis. There exists a common eigenbasis in which they are diagonal. So I can now write the spectral decomposition or the eigenstate decomposition as sum over I, Ri, II, and this is diagonal in the same basis with different eigenvalues presumably, but it's the same basis. I don't have to look for two different bases like I did here in the case that they were mutually orthogonal, right? So now it's the same set of eigenstates, and then what do you have? Your fidelity function becomes trace square root. Remember, the eigenstates of square root of a Hermitian operator are the same as the eigenstates of this. So when I do the spectral decomposition, rho to the half is simply an operator whose eigenvalues are square root of this and diagonal in the same eigenstates, the same eigenbasis. So this becomes square root Ri Si square root Ri II, right? So I hope you can work this out, because you will simply have, you'll start with two sums. When I have rho to the half, sigma rho to the half, you can even write down three sums over ijk, but all of them will have to collapse. So this, remember, these are let's say rank 1 for now. Of course, you can have a case where these eigen projectors are higher rank, but you can always decompose it in some rank 1 form. So this trace is 1. So this then gives me, oops, I forgot the sum. Okay. So this then gives me sum over I square root Ri Si, right? Now what is this? So remember that trace of these density operators must be 1. So trace rho is the same as trace sigma is 1, implies that sum over I Ri is the same as sum over I Si is 1. So the Ri and Si form a set of, they form a pair of probability distributions. And so this is actually what is called the Bhattacharya distance. I don't know if people who do classical information or classical error correcting codes and so on have seen this measure. Anybody who's done some probability theory would have seen this measure. This is called the Bhattacharya distance between two probability distributions, the Ri distribution and the Si distribution, right? This is also sometimes called the Beer's metric. Different forms of the same thing. But essentially, it's a kind of classical metric between a pair of probability distributions. And when rho and sigma commute, you recover this limiting case of the classical distance between two probability distributions. So all of this tells you that this is a well-defined measure, and it's a good measure to use to analyze how close two quantum states are, and in particular, this case where one of them is a pure state and the other is a mixed state will be useful for us to look at the performance of an error correcting code. Any questions? So the last point that I want to mention with respect to fidelity, and this I will not prove, this will be homework for you, is a question that somebody should have asked me, but nobody asked me. The way this measure is defined, right? You look at this, I've said f of rho sigma is trace square root rho to the half sigma rho to the half. What is f of sigma rho?
It's the same.
Why is it the same? How do you know that they are the same? So this has to be proved, okay? And that will be part of your next tutorial. I'm sorry, it's been a bit, I got delayed in uploading it, but hopefully by tomorrow morning, the tutorial should be up on Moodle. But it turns out that indeed they are the same. So F is actually symmetric in its arguments. The rho and sigma are the arguments, right? And this will be proved in tutorial 2. Okay. So indeed, the answer is yes. And while it's not obvious looking at the states, yeah, you can either already read up Nielsen-Chuang and work through the problem, but it's basically a Nielsen-Chuang problem, which shows how these two quantities are actually the same, right? The measure is indeed symmetric in its arguments. You don't have to worry about which one you put first and so on. Otherwise, it wouldn't make sense as a distance measure. Okay, so back to analyzing the 3-qubit code. I think I have about 10 more minutes. I'll stop in another 5 minutes, where I just want to discuss what is the fidelity that you get if you use the 3-qubit code in the presence of bit flip noise. Okay, so let's do the last bit of analysis for the 3-qubit code, and tomorrow we'll start looking at more general purpose error correcting codes. So the last bit today is fidelity analysis of the 3-qubit code. So the first thing I want to discuss is what is the fidelity of the raw unencoded qubit we call this the bare qubit in the presence of bit flip noise. So I have a single qubit, which, let's say we start with a pure state, and then this goes to 1 minus p psi psi plus p x psi psi, right? It's some arbitrary single qubit state. So this is what I will call sigma. And I want to look at f of psi comma sigma. And it's easy to see what this is, right? So if you want, we can do the f squared, because we saw that the f comes with a square root, right? It's for between a pure state and a mixed state. This is what it looks like. So this is the expression we will use, the f squared expression. So let me call this as something else, equation 1 maybe. So I will use equation 1 as I'll make that my primary fidelity definition. So this is nothing but psi sigma psi, okay, which is 1 minus p plus p psi x psi mod squared or squared, it doesn't matter, right? This is what we have. Now you see, this is a state dependent quantity, right? So this is state dependent. And of course, we know this already because we looked at the fact that this noise channel, the single bit flip noise channel, actually has fixed points and all that. So if psi were an eigenstate of x, then it remains unaffected. We already saw that it's an invariant state. It's a fixed state, right? And how can you check that? If it's an eigenstate of x, what happens? What is here becomes plus or minus 1. And then the square of that, and then you have 1 minus p plus p, so your fidelity is actually 1. On the other hand, if your state was one of the z eigenstates, which is the 0 or the 1, then you can see that what you have out here is actually 0. So the point is, we need to somehow find a measure that captures how well the states are preserved, or how much are the states disturbed, if you want to think about the other way, without reference to a particular state. So this measure, which is often used in error correction, is what is called the worst case fidelity. Actually, you can do one of two things, right? You can either talk about the average fidelity, wherein you take an average of this expression over all pure states. Now, such an average has to be clearly defined. That takes us to a completely different topic in quantum information, which is how do you, what is the measure over pure states, and how do you do an averaging over pure states, R measure, etc. So this will lead us to a different sort of issue and that's another very interesting topic one can look at in quantum information itself, right? But what we're going to focus on for error correction is what is called worst case fidelity. So this is then a min over all states of this fidelity expression. Why do we use worst case? Because having a certain worst case fidelity, it gives you a lower bound on this function, right? And it tells you that no matter what state you pick, its fidelity is going to be at least this much, right? It will certainly be above this most of the time, or it will be at least this much. So it gives you a kind of minimum guarantee that your fidelity is going to be above a certain number. So what would be the worst case fidelity in the case of this single qubit bit flip channel? So can you tell me what is the worst case fidelity here? If you minimize over all psi, what do you get? So the psi dependence is only in the second term. And what is the smallest value the second term can take? 0, exactly. So this is just 1 minus p indeed. So this is the worst case fidelity for the unencoded qubit. Now, 2 more minutes, I will compute the worst case fidelity for the encoded qubit. Actually, I will say after, not just encoded, but after the 3 qubit QEC protocol, what happens? So whatever was your initial state has gone to the encoded state. So now let's look at psi logical, which is the encoded state. So this is some arbitrary state of this form, right? And this logical state has gotten transformed to some mixed state, which looks like what? So now you have all the possible errors that have happened, right? So what is the final state? It's going to be, so generally a sum like this, right? But over and above the noise, you have also done the recovery, okay? And whichever of these error terms correspond to single qubit or no error, you are back to the original state. So this is what this state is going to look like. 1 minus p the whole cube is the prefactor behind the identity term. So it's going to be just this plus 3p 1 minus p the whole squared. Again, projector onto psi psi, because this corresponds to the single qubit errors, which are all perfectly correctable. So the single qubit errors have all been corrected perfectly, and the density matrix corresponding to that errored state has been mapped back to this pure state. But of course, the rest of it is a density matrix because you still now have the 2 qubit error terms. And the 3 qubit error term. Note, however, that whatever is here, now the whole thing is a positive semi-definite matrix, right? And whatever you have here is all going to be of order p squared or higher, right? Okay. So now how do we get to the fidelity? So the fidelity, I'm again going to use the square, okay? And I'm just comparing the fidelities in the logical space itself. It doesn't matter because, okay, this is another thing which we should check, which is that the encoding and decoding are just unitary operations, you remember. So whether I compare the fidelity between the two logical states or the encoded states, or the come back to the single qubit space and compare the fidelity, it shouldn't change. Okay, so this measure is invariant under unitaries. Okay, I'll see if I can put in something about this also in the tutorial for you to get a feel for this. But so what is this? So this is now again psi rho psi. I've only listed the first two terms. The first two terms give me a perfect overlap with psi. So that is just 1 minus p the whole cube plus 3p squared, 3p 1 minus p squared plus overlap of psi with the 2 qubit and 3 qubit error terms. But note that these are all some set of positive operators, right? Every term in this kind of a Krauss decomposition is a positive operator. So everything that I'm sandwiching between the psi is a positive operator. So this is greater than or equal to 1 minus p the whole cube plus 3p times 1 minus p squared. And this, as you know, is nothing but 1 minus 3p squared plus 2p cube. This is what we already worked out. So this gives me a lower bound, and I automatically get a state independent lower bound on the fidelity. So effectively what I have already is the worst case fidelity. I'm bounding all of these terms. These are all positive terms. So I'm just saying that the whole thing is something greater than this, right? So this is effectively the worst case fidelity. So the min over psi, the smallest that these can all be is 0. They cannot be negative, right? So this is similar to what we had even in the single qubit case in terms of minimizing that set of terms. But the worst case fidelity, therefore, is 1 minus 3p squared plus 2p cube. So you see that while the worst case fidelity in the unencoded case, the leading order was order p, you now have the leading order here to be order p squared. So it's of the form 1 minus something order p squared as opposed to 1 minus something order p, which is the case of the physical bare qubit, the unencoded qubit. So this is again the argument for why error correction is useful, right? It removes the order p term, which is the higher order term, and the leading order becomes an order p squared. So once again, you can do the comparison and you will say that QEC is successful provided this encoded or the post error correction worst case fidelity should be greater, right, than 1 minus p. So the condition for that you will see again is nothing but p less than half, which is the same noise threshold that we had from the simplistic error analysis without going into states and fidelity and all of that, right? So it's the same noise threshold. The 3-qubit code is successful provided the single qubit bit flip probability is less than a half. Okay, let me stop here. Questions? All right, if there are no questions, you can leave. We'll meet again tomorrow and we'll look at extending these ideas now to other noise models. This is just bit flip. So what about other noise, phase flip, etc.? General purpose error correcting codes and all that. Okay. Yeah. See you all tomorrow.